Welcome back. In this fifth segment, we're going to look at a second example of a function f of n for which we're going to try to find a good upper bound. Remember that f of n represents the runtime or the time complexity of some algorithm, and we're trying to find an upper bound for this runtime, and this upper bound should be as low as possible. It should approximate the function f of n as closely as possible. That's what we mean by a good upper bound. So in the second example, the function f of n is defined as follows. Again, it's the addition of two functions, the first one of which is a product, and the second one of which is this polynomial of degree 2. So as in the previous example, we're going to consider the components of the function f of n one by one from left to right. So the first term we consider is the polynomial term 2n plus 1, which has degree 1 and therefore is big O of n. Let's record that and move on to the second term in the function f of n, namely this one. Now this one is not a well-known reference function. It's a little bit complicated, so again we're going to do a little bit more work to find an upper bound for that term. Let's consider first the argument of the logarithm function. We're going to upper bound every term in this addition by n cubed, which is the largest power of n in this polynomial. Of course, n cubed is less than or equal to itself for any value of n. This term is also upper bounded by n cubed because if n is greater than 5, then n times n squared is greater than 5 times n squared. Therefore, this term is also upper bounded by n cubed as long as n is large enough, say larger than 5. Similarly, we can find a value of n for which n cubed is greater than or equal to 12, so we can upper bound this term by n cubed as long as n is, say, greater than 3. So in conclusion, we found an upper bound on this term, which is equal to 3 times n cubed. Now we can use or apply the logarithm function, which is a strictly increasing function, to each side of the inequality. And let's remember that n must be greater than 5, of course, for this upper bound to work. When that's the case, the logarithm of this function then is less than or equal to the logarithm of 3 times n cubed. Let's rewrite this term using the definition of the logarithm function as log 3 plus 3 times log n. Let's upper bound this term now. If n is greater than 3, then log n is greater than log 3, and therefore this term is less than or equal to 4 times log n, as long as n is greater than 3, say. So in conclusion, the term that we're interested in here was found to be upper bounded by 4 times log n, as long as n is large enough. So by definition then, this term is big O of log n. Now all we have to do is to consider the multiplication of these two functions and use the appropriate theorem to infer that the first part of the f of n function is big O of n times log n. Now we can turn our attention to the second term in the addition. 2n squared is a polynomial function of degree 2, so it's therefore upper bounded by n squared, or it's big O of n squared. And finally, we can use the theorem about the addition of functions to infer that f of n then is big O of the maximum of this function and that one. Again, n squared is going to dominate n log n, and therefore f of n is big O of n squared. Now before we move on to the next example, let's make an interesting observation. Notice that in the previous example we had the logarithm of a polynomial of degree 2. Here we have a polynomial of degree 3 inside the logarithm. And in both cases, the resulting function was big O of log n. So you can follow the same reasoning that we just did for these two examples, and you'll realize that it doesn't matter how big the degree of the polynomial. You can have a polynomial of degree 100 or 1000. In other words, you can have a function that grows really fast. Once you apply the logarithm function to it, you get a function that ends up growing pretty slowly, namely like the logarithmic function. So the interesting thing here is that the logarithmic function grows so slowly that even when its argument grows really fast, you still end up with a logarithmic growth in the end. Now, the next and last example of a function for which we have to find a good upper bound is one that I want you to work on your own. So here our goal is the same. The methodology is pretty much going to be the same as on the two previous examples, but you will have to work out the answer for the following function. So example 3 is the function f of n equals to 3n times log of n factorial plus n squared plus 3. Make sure you review all of the results we already discussed about the growth of functions, the factorial function, and in particular the log of n factorial, and I'm confident that you will be able to find a good or best upper bound for this function f of n.